We have an isosceles triangle ABC. D is on side BC, and we extend AD to meet the circumcircle again at E. The point F is on circumcircle of ABC such that angle DFE is 90 degrees. Finally, we extend the line FE to intersect the rays AB and AC at X and Y respectively. We want to prove that angle XDE is equal to angle EDY. The first thing we should notice is that the condition that angle DFE is 90 degrees is the same as the fact that F lies on the circle with diameter DE, because everything on the circle is a right angle with respect to D and E. So we can actually notice a bit of a significance of the points X and Y here. Specifically, let me draw something out here. If we have a circle, and then we have 2 points on the circle, let's call these points 1, 2. We draw another circle and let the 2 intersection points be 3 and 4. So let's let these 2 lines meet somewhere. Let's say here, which we're going to call X. Notice the similarity here. We have that 1 is just B, 2 is A, 3 and 4 are F and E, and X is X. So we know that if we draw any line from X to intersect this circle at points 5 and 6, by power of a point, x3 times x4 is equal to x5 times x6. But x3 times x4 is also equal to x1 times x2 by power of a point on this big circle. So x1 times x2 equals x5 times x6, and then 1, 2, 5, 6 are indeed concyclic. What this means is that next time whenever we see a configuration like this, we can just imagine that any line we draw from X to this small circle, the 2 points that are created are always concyclic with 1, 2, because X will be the radical center of this circle, and whatever circle that passes through these 4 points. So this is a very useful knowledge we should always keep in the back of our mind, especially when we come across a problem like this, where we can clearly see that something can be done with this fact. And it's even more helpful when one of these points we already know, because then we can just know that this point is concyclic with these 3 points. Since we already know this point, let's call it star, we also already know these 3 points, and so we can actually get more useful information about this. And what's cool about this is that we can actually encode all of the information of X into this intersection point, because we can always just construct X now by drawing this circle if we know this point, and then we can define X as the intersection between these. So we can encode all of the information from X to this new point. Now let's see how we can apply this knowledge into our problem here. And as I've already mentioned, X corresponds to X in our problem, and we can just connect the line XD to intersect this circle at, let's say, K. So we're going to encode all the information from X to K. Similarly, we can draw DY and encode all the information from K to this intersection point, which we will call L. To prove that XDE is equal to YDE, we can just prove that KDE is equal to LDE. And as we see here, we actually don't need X and Y anymore. We just want to prove that these 2 angles are the same. But if we look at this, since K and L both lie on this circle, these 2 are both right angles, and in order for these 2 angles to be the same, these 2 triangles, KDE and LDE, have to be absolutely congruent. Okay, so what we can do here is that let's draw this line AK and AL. So let's think about what these 2 angles might be. Since we've already concluded that ABKD are concyclic, we know that AKD is just equal to ABD, so it's this angle, and ALD is equal to ACD, which is this angle. But since ABC is isosceles, these 2 angles are the same, and hence these 2 angles are the same. So let's actually draw out what's happening here. We have this line, which is the line A, D, and E, and then we have a certain point K over here, so that this is actually a right angle, and we have a certain point L over here, and this is also a right angle, and we also know that these 2 angles are equivalent. Now, we might make the guess that these two triangles are actually just reflections of each other across the line AE, and we're totally correct. But we have to somehow prove that. Well, first of all, we can use the ratio lemma, which says that KA over KE is equal to ED over DA multiplied by sine of this angle over sine of this angle, or something like that. But actually, let me write it out a bit more rigorously. Let's say this angle is alpha and this is 90 degrees, then we have that sine of alpha over sine 90 degrees is equal to AD over DE multiplied by KE over KA. And similarly, we can write the same expression on this side to get that sine of this angle over this angle, which is the exact same as this, is equal to AD over DE multiplied by LEL over LA. Hence, this to this is equal to this to this. But we also know that their angles are the same. Hence, the triangle AKE and the triangle ALE are actually similar. But we also know that they share the side length AE, hence they are indeed congruent. Okay, they're congruent. So they're just reflections of each other across the line AE. Now, this configuration is actually quite helpful, so it wouldn't do you any harm to kind of memorize this, which is that whenever you have a line here, let's say AE, and a point D, if we extend anything from D out here and somehow this angle equals this angle and this angle equals this angle, then we know that everything in this triangle, or in this, I guess, quadrilateral, is as congruent as you want it to be. Or that, for example, this quadrilateral is directly symmetric about the line AE. So back to our original problem. We have proved that AKE and ALE are indeed congruent. They are reflections of each other across AE. So obviously, KDE equals LDE, and so XDE equals YDE. And that is exactly what we wanted to prove, so the problem is done here. Now, I really like this problem because it was really rich in takeaways, and I'm going to summarize it for you with two takeaways. Takeaway number one is to spot the significance of the point X and Y, which was, as we've actually talked about in quite much detail before, if we have some configuration like this and the intersection point here, this point is actually very useful because it is a radical center of this circle, and some other circle that we can construct later. Specifically, any line we draw here, these four are concyclic, which is very helpful. And it is the radical center of these three circles, and we can encode all of the information from X onto one of these points if we know what the other point is. The second key takeaway here was this configuration, where if we have something like this with D going out to K, D going out to L, and somehow these two angles are the same, then we have that this entire figure is symmetric about AE, which can turn out really helpful as it is in this problem.